Hello friends, welcome back. Today we are going to be looking at how to remove an element from a binary heap. So over here we have this set of instructions that we want to perform on this binary heap. By the way, this is a min heap, meaning that the value of the parent node is always less than or equal to the value of the child nodes. So as you can see, 1 is less than 5, 5 is less than 8, 8 is less than 13. Okay, so you can see that the values of the parents are always less than the value of the children. Okay, all right. Also, if you check out the this set of instruction, we have one called the poll operation, and we have one called the remove operation. So the poll operation means that you want to remove the element with the highest priority, okay? And that means that you want to remove the element at this position, okay? So if this binary heap was represented using an array, that will be the element at the 0th index, okay? So we also have the remove operation. So for the remove operation, we don't know the position of the element that we want to remove. So the first thing we have to do is to look for the position of that element first, then we are going to remove that element, okay? So let's start. So the first operation here is the poll operation, okay? So we want to remove this element. So the first thing to do is that we have to swap this element with the last element in the queue, and that is this element over here. Okay, so we're going to perform a swap like this. Okay, so now we can remove 1. However, after this removal, you can see that we are no more satisfying the binary heap invariant, okay, or the binary heap property. So what I'm trying to say is that 10 is greater than 5, okay, which is invalid for a min heap. For a min heap, the parent must always be lesser than the child, okay? So what we have to do is to bubble 10 downwards, okay? But the question here is, are we moving towards the left direction or towards the right direction? Okay, so the answer to that is that you have to always pick the least among the children. Okay, so in this case the least is 1, so you have to bubble towards the right direction. So if these two were equal, then you can move towards any one of them. Okay, but just make sure you pick a default position if the two children are equal. So you can pick the left and you can pick the right. Okay, but if they are not equal, then pick the least. So the least in this case is 1. Okay, so we're going to move towards the right direction like this. Okay, so now we are still not satisfying the binary heap invariant. 10 is greater than its children. Okay, so we're going to bubble towards the left direction like this, then like this. All right, so now the binary heap property is satisfied. All right, so let's move towards the second instruction, which is to remove 12. Okay, so now we don't know the position of 12, so we have to check each position and to see if the element at that position is 12. Okay, so we're going to start from the beginning like this. So we check this again, then we keep moving like that, then eventually we are going to find 12. Okay, so once we find 12, then we can swap 12 with the last element in the queue, in the priority queue, which is 3 in this case. Okay, so we can just swap it like that. We can remove 12. Okay, and if we check this, we are not satisfying the binary heap property, anymore because 8 is greater than 3. Okay, so we have to swap these two like this. Okay, also if you check 3 and 5, 5 is greater than 3, so this is invalid, so we have to swap these two like this. Okay, so now at this point 1 is less than 3, okay, and 3 is less than its children, right? So we have been able to satisfy the binary heap property. So the operation is complete. So let's move to the next operation, which is to remove 3. Okay, so first we have to look for the position of 3 like this. Okay, so 3 isn't far away. This is just a two-step check. Okay, so now we can swap 3 with the last element like this. Okay, so now we can remove 3. Okay, and there is a question here. Okay, so are we going to bubble up or bubble down? Well, if you check this binary heap from the top, you will discover that we have been able to satisfy the heap property from the top because 1 is less than 15. Okay, but if we look downwards, you will discover that 15 is greater than its children. Okay, so we have to bubble downwards because the binary heap property is not satisfied in the downward direction. So we're going to pick the least child, which is 5, and then we swap like this. Okay, then we pick the least among these two, which is 8, then we swap like this. Okay, so now we have been able to satisfy the binary heap property. Okay, so let's check out the next operation, which is the pole operation. Okay, so now for the pole operation, we already know the position, right? So we can swap it with the last element in the binary heap like this. Okay, so we can remove 1 like this. All right, so now we have to satisfy the binary heap property, so we bubble 10 towards the right direction because 2 is the least child, right? So like this, then they are equal, right? So we can just pick anyone, but I'll pick the left in this case. So I'm going to swap like this. All right, so now let's check out the last operation over here. So we have to look for the position of 6 because we want to remove 6, right? So we start checking. Okay, we check here, we check here, we check here like that. Then okay, so eventually we are going to find 6. So once we find 6, we are going to swap it with the last element as usual like this. Then we remove 6. Okay, so at this point 5 is less than 7, right? And 7 is less than 11. So this binary heap is the binary heap property is satisfied. Okay, so we can leave it like this. All right, now if you take note, you will discover that for the pole operation, okay, we didn't have to search for the position, right, of the element we want to remove. Okay, we only had to reset the binary heap after a removal for a pole operation, so that takes a log n time. Okay, but for the remove operation, we have to first check the position. We have to find the position of the element that we want to remove, and that takes n time complexity. It takes n time. Okay, so this means that at the worst case, we have to check all the elements. So imagine we have 1 billion elements in the priority queue, right? So we have to check, and you want to remove the 1 billionth element. So that means you have to perform a billion check, and that is not effective. Okay, so if you are like me, you will think of a much more efficient way to perform this operation. So there is an efficient way, and that is what I'm going to be showing you in the next video. So make sure you subscribe to this channel so that you can be notified when the new video comes out. Okay, so I'm going to see you in the next video. Bye.